All right, in this video we need to talk about something called enthalpy. Enthalpy is simply a measure of how much energy is absorbed or released during a reaction. So for this particular example, this is essentially literally the reaction of how like rocket fuel works. A lot of space shuttles, they have one tanker of hydrogen, one tanker of oxygen, and the only waste product is water. But you get a lot of energy out. Okay, so a couple things to point out here. One is the idea of something called endothermic and exothermic. Let's actually talk about exothermic first. Exothermic is when energy is released by a reaction. In other words, it gets warm. It releases it to the surrounding area. Okay. We're going to put it energy released as heat. In this chapter, we're pretty much only going to worry about whether heat is absorbed or released. In the next chapter or two, we actually are going to deal with the idea of what happens if things absorb and release light. Right now, we're just worrying about heat. Okay. This is also, delta H is the symbol for enthalpy. Exothermic is the idea of it releasing energy. The reaction occurs in, like, let's say a beaker. Okay. And what happens is basically it produces enough heat that the heat releases to the surroundings. Okay. And somebody by default decided a long time ago that this means that delta H is going to be negative for exothermic reactions. Okay. All this means is that it is losing heat. Okay. Endothermic is the opposite. So this is when energy is absorbed by a reaction. What this typically means is that you have to heat it up. You have to put heat into the reaction to make it occur. So this would be a positive delta H. I will tell you that endothermic is way, way more common. Okay, and here's why. Typically what we're looking at is the energy difference between the reactants and the products. So I'm going to draw a little diagram here. Okay, so what we have on this axis is energy, and this is just reaction progress. It's basically just time. Basically, as the reaction occurs, this is what's happening. So typically what we do is most exothermic reactions, which are the most common option, typically what we have are the reactants are at some potential energy, okay? We're just gonna label it reactants. We're gonna keep it generic here. And then what happens is the products tend to be more stable, okay? This is the example like in the last video, where I said that basically if you took something like gasoline, it is more reactive, it has a higher potential energy, and if you throw a match at it, it will become more stable products like carbon dioxide and water. Okay, so the products tend to be more stable. The difference between these two is our delta H value. And because from the beginning of the reaction to the end, it dropped, delta H is negative. Okay, but like we saw earlier, is that basically in the previous video, is that even if you have something that's unstable, you have to put in energy to get it to be released as kinetic energy. So typically, most reactions kind of have this little bump in the middle. Okay, this bump gets this little symbol. It's called a double dagger. I don't know. I didn't come up with that name. It means transition state. And it's just somewhere in between reactants and products where like the bonds are kind of half formed, half broken, like it's in between reactants and products, okay? And the difference between the reactants and the top of this is something called the activation energy. We'll do it like this. E sub A equals activation energy. And my pen is dying. Well, we're about to switch colors. Activation energy. Okay. What this is this is how much energy it takes to break these things apart so that they can reform as products. Okay, so if you had something like gasoline, this activation energy is very, very small. A match is not a lot of energy. You can throw a match or a spark into a thing of gasoline, it will easily get over that energy barrier and become products, violently so. Okay, but if you had something like graphite turning into diamonds, diamonds are more stable, graphite is more reactive, but the activation energy is like through the roof, which is why it takes, lava level temperatures and mountains worth of pressure pushing down on coal to convert it to diamonds, because the activation energy is so high. So both of these are important. In this chapter, we're mostly focusing on this delta H. Okay, so, but just because something is going from more reactive to less reactive doesn't mean the reaction will always occur. Sometimes the activation energy is too much of a barrier and messes everything up. Okay? So, let's figure out what we're going to do with this. Why do we need to know how this works? Let's do an example that involves the stoichiometry here. The balanced equation is important. Okay, so honestly, we'll just use this one. This will work. State symbols are not that important, but I'm going to include them anyway. Okay, so this is what happens when you light a Bunsen burner. Methane, CH4, reacts with oxygen. Both of these are very reactive. And your products are carbon dioxide and water. Okay? The delta H for this is negative 890 kilojoules. Okay? The way to interpret this is that 1 mole of methane plus 2 moles of oxygen forms 1 mole of carbon dioxide and 2 moles of methane, or of water, and 890 kilojoules of energy in the form of heat should be released. Basically, it's a fire. Okay, but it is based on moles. Okay, so similar to the stuff we saw when we did stoichiometry, like limiting reactant problems, and when we did titrations, is if you have starting amounts of these, you can actually figure out how much energy is going to be released. So we want to know how much heat is released when burning, I don't know, say 25.0 grams of CH4. Okay, so, question. All right, so how much heat is released? Well, this tells us that for every 1 mole of this, we should get this much energy. It's almost like the mole ratio type of thing. But this is in grams, so the first thing we're going to have to do is convert this to moles. So you're going to add up a carbon and 4 hydrogens using the periodic table. Oops. Okay, so carbon is 12.001, or 011, plus 4 times 1.008. Okay, and our value is 16.043. That's grams per mole of CH4. Okay, if there was a number in the front here, let's say there was like a 5 in the front. For every 5 moles, you would get that. But because there's a 1, we can just write for every 1 mole of CH4, we should release 890 kilojoules. Okay, but this is based off the balanced equation. So if this number isn't, whatever coefficient is in the front here will go in the bottom. So if there was a 3 here, this would be a 3 in the bottom. Okay, but otherwise we just type everything in, see what we get. So 25, let's see if I can do it like this, 25.0 divided by 16.043, it equals times 890, and the answer is, I guess, 3 sig figs, negative 1390. The line over that, because that's our last sig fig, kilojoules. Now, I will tell you that the negative sign is almost redundant here. The negative is just telling you that the energy is being released. So the question says how much energy is released. You can't actually have negative energy. This just means that the energy is being released. So basically you have a fire and it's getting hot. So if you wrote an answer of positive 1390 and it said how much is released, as far as I'm concerned, that's correct. Can't guarantee Sapling isn't going to freak out about those details, but as far as I am concerned, this negative just tells you that it's being released. It doesn't mean anything else. Okay. So this is based on this balanced equation. Okay. If we look at a different example, so let's say we've got this reaction. Mercury 1 oxide is a solid, apparently. And if you have 2 moles of that, it could break down into 2 moles of mercury, which is a liquid, and O2. Okay? Mercury's a liquid at room temperature. Okay. And this has a delta H of positive 181.7 kilojoules. Okay? And this time what we want to know is, okay, so what this is telling us is that this compound is breaking down into the individual elements that made it up. It's decomposing. This is a decomposition reaction. Okay, this was an example of a combustion reaction. This is a decomposition. So what we're finding out is that it takes 181.7 kilojoules to neutralize that. Sorry. Not COVID. All right. But in theory, you could take these things and react them. So what we find out, though, is that if you reverse this reaction, so let's say we take these things and we decide we're going to react them, we could, in theory, form that product, or what was our reactant. And because going this way required 181.7, if you reverse things, it's going to release 181.7. So the important thing is basically your delta H is directly connected to the balanced equation that you write it with. Okay, so I couldn't just tell you, oh, the combustion of CH4 is negative 890. You have to have the full balanced equation. Same thing here. The reaction written this way has a positive 181.7 value. The reaction written in reverse has a negative 181.7 kilojoules. Okay. Similarly, we could also have this reaction. Okay. So, I guess I could label a few things here. So this was reversed, and this was reversed. Okay. This one, everything was halved, or divided by 2. Right? This was 2, now it's 1. This was 2, now it's 1. This was 1, now it's 1/2. So divided by 2. Okay. The same thing is going to happen to delta H. So we're going to take 181.7 divided by 2. And our value is positive 90.85, I guess. Keep our sig figs right. Okay. But the idea is whatever you do to the balanced equation, the delta H does the corresponding thing. So if you flip the reactants and products, the sign changes. If you doubled everything, this would double. If you have everything, this halves. Okay, so the balanced equation has to be written with your delta H, otherwise it doesn't mean a whole lot. Being able to flip and manipulate these equations is going to be really useful later in this chapter. All right, thanks.